Imagine holding a silver box that easily fits in the palm of your hand, yet possesses enough raw computing power to outperform industrial workstations that cost thousands of dollars. For years, the desktop computer market has followed a rigid, predictable script. If you wanted elite performance, you had to accept a massive, power-hungry tower sitting under your desk, humming with loud cooling fans. But behind closed doors at Apple Park, an aggressive engineering shift has occurred. Apple didn't just iterate on their compact desktop line, they re-engineered the very laws of silicon efficiency. This isn't a routine spec bump. This is the moment the compact desktop transitions from a convenient consumer device into an absolute powerhouse. Welcome to the era of the Apple Mac Mini M5. If you think you know what to expect based on previous hardware refreshes, you are only looking at the surface. The real narrative surrounding this release isn't about slightly shorter rendering bars or a minor jump in clock speed. It is about a radical breakthrough in chip packaging, an architectural pivot toward localized, non-stop artificial intelligence execution, and a direct challenge to high-end custom PC rigs. Today, we are pulling back the curtain on the supply chain shifts, the leaked engineering data, and the precise mechanical reasons why this machine is creating a massive dilemma for creative professionals and studios worldwide. If you want to understand where desktop computing is going, you need to look very closely at the hardware breaking records right now. To truly understand the massive engineering leap of this machine, we have to look at the global silicon crisis that completely altered Apple's launch timeline. Insiders point to a perfect storm in the advanced semiconductor industry. A massive bottleneck at TSMC's fabrication plants, combined with an unprecedented global shortage of high-bandwidth memory chips. This crisis forced Apple to hold back, refine, and supercharge their architecture. They used that extra time to shift the chip to an enhanced, bleeding-edge 3nm process. This isn't just about shrinking transistors. It's about altering the physics of power delivery. The silicon die inside this machine packs an unprecedented density of transistors, allowing it to execute complex instruction sets at speeds that make previous generations feel sluggish. This advanced fabrication process is the foundation for the headline feature of the M5 architecture, the dedicated neural accelerator integrated into each individual graphics core. In previous generations of Apple silicon, the neural engine sat as a distinct, separate block on the chip, handling AI tasks sequentially. By embedding specialized neural accelerators directly into the GPU cores, Apple has created a massive parallel processing highway. The architecture allows the machine to handle complex mathematical matrices simultaneously. We are looking at an astronomical jump in localized AI performance compared to earlier chips. This means heavy language models, neural filters, and complex coding algorithms don't just execute faster. They run completely locally, completely instantaneously, and without sending a single byte of data to an external cloud server. This deep integration of localized processing explains why major enterprise corporations and creative houses are quietly buying these compact desktops by the thousands. They aren't using them as standard office workstations. They are deploying them as dedicated, 24/7 local